everyone, ready for some physics?
Always.
Good, because today we're diving deep into the photoelectric effect.
Ah, a classic.
But here's the twist. We're exploring an alternative way to understand it. Forget photons for a sec.
Oh, this is interesting already.
We're talking about resonance.
Now that's a concept we can all relate to.
Exactly. So before we get into electrons going wild, what exactly is resonance?
Well, in simple terms, resonance happens when a system, let's say a guitar string.
Or like a kid on a swing.
Perfect example. So when a system is exposed to a force vibrating at its natural frequency, things get amplified.
Like pushing the swing at just the right time to get those huge swings.
Exactly. It's all about hitting that sweet spot, that frequency match.
So it's not about how hard you push, but when you push.
You got it. And it's not just swings and guitars. Think about how a microwave heats your food.
Wait, is this where resonance comes in?
You bet. Microwaves emit waves at a specific frequency that just happens to match the natural frequency of...
Don't tell me. Water molecules.
Bingo. Those waves get those water molecules vibrating like crazy, generating heat and warming up your leftovers.
Okay, that's cool, but resonance has got to go beyond just nuking leftovers, right?
Oh, absolutely. Yeah. Think musical instruments, like two guitars tuned exactly the same way, side by side.
Okay, I'm picturing it.
Now imagine plucking a string on one guitar.
And it magically makes the other guitar play the same note.
Sort of. Those sound waves can actually cause a corresponding string on the other guitar to vibrate too.
But only if they're tuned the same, right?
Exactly. It's like those sound waves are searching for something vibrating at the same rate, and when they find it, resonance.
And it doesn't matter if you pluck the string gently or go all out, a different string won't vibrate, right?
Well, a louder sound just means more energy, but it won't change the frequency. It won't make a differently tuned string suddenly resonate.
Because it's all about that frequency match. Okay, I'm starting to see where you're going with this, but how does all of this connect back to the photoelectric effect with electrons escaping from metal?
That's where things get really wild.
Wilder than a guitar playing itself.
Way wilder. See, with the photoelectric effect, instead of microwaves and water molecules, we're dealing with light waves and electrons, those tiny particles that carry electricity.
Okay, I'm with you so far.
So these electrons, they're not just bouncing around randomly inside atoms.
They're not.
Nope. They exist at specific energy levels. Think of it like they can only be on certain floors of a building.
All right, I'm visualizing an electron stuck on one floor.
Perfect. Now, along comes light. Light waves. They carry energy, right?
Right. Light equals energy. Makes sense.
So if a light wave with just the right frequency hits an atom, it's like sending an elevator to that electron's floor.
The electron hops on, goes up a level, more energy.
Exactly. But here's where the photoelectric effect gets really mind-blowing. We're talking about the electron getting enough energy to completely escape, to break free from the metal entirely.
Ah, so it's not just moving up a floor, it's like blasting a hole through the roof.
Exactly.
Ah.
And the traditional way to explain this is with photons, these little packets of light energy, knocking those electrons loose.
Like tiny little bullet particles of light.
Yep. But the source material we're looking at today, it suggests there might be more to the story.
Hold on, you're saying we might not need those photon bullets? Our elevator analogy works even for escaping electrons?
That's exactly what this paper, The Photoelectric Effect Without Photons, is proposing.
No photons. That's a bold statement. Who wrote this?
Willis E. Lamb. He dives deep into this idea that we might not need to think of light as particles in this case. Instead, he says we can stick with classical electromagnetic fields, light waves interacting with those energy levels of electrons.
So we've got our electron on its floor, light waves are still elevators, but we can ditch the photon bullets.
That's the gist. And here's where it gets really interesting. Lamb actually derives Einstein's famous photoelectric equation, the one that everyone uses. But he does it without ever mentioning photons.
Wait, he found a way to explain one of the most fundamental physics equations without one of the core concepts it's based on.
It's like he found a back road to a place everyone thought you could only get to by highway.
That's crazy. So are we saying light isn't acting like a particle here? Or can it be both a wave and a particle?
That's the million-dollar question. And Lamb's paper isn't alone. There are others out there, like antiphoton and the concept of the photon, that also poke holes in the traditional solely particle-based explanation.
So we're questioning the very nature of light itself. My head's spinning. Okay, so we've got electrons on the floors, light wave elevators, and now we're questioning what light even is. What's next?
Okay, but even with all this talk about photons and waves and electrons on different floors, there's this one thing I don't quite get.
What's that? It's about the electrons escaping. If light can just give them energy, why don't they just fly off all the time? Like, shouldn't any light make them escape?
Ah, that's where the work function comes in. It's a crucial concept.
Work function. Sounds intimidating.
It's simpler than it sounds. Think of it like, imagine you're trying to push a ball up a hill. Steeper hill. More energy you need, right?
Makes sense. More effort for a steeper climb.
The work function is kind of like the steepness of that hill, but for electrons trying to escape the metal, it's the minimum energy they need to break free from the surface.
So it's like a barrier they got to overcome to become free.
Exactly. And this is where the frequency of our light fader comes back in. Remember, the electron needs to hit a specific floor to escape, right?
Right. The right frequency to reach a high enough energy level, like hitting the top floor button.
Exactly. But even if it gets to a higher floor, it still needs enough energy to bust through the ceiling and get out of the building entirely.
So if the light's frequency is too low, it's like the elevator doesn't go to the top floor no matter how many times the electron rides it?
Precisely. The electron might jump around on lower floors, but it won't escape the building. It's stuck.
Okay, so frequency is key. But what about how bright the light is? Does that matter?
It does. That's like having more elevators all arriving at the same time. Brighter light, more waves, more chances for electrons to catch a ride.
So brighter light means more opportunities for escape, even if they don't all make it.
You got it. But remember, if none of those elevators go to the top floor, if the frequency isn't right, none of the electrons are escaping, no matter how many try.
So it's like this. The right frequency is the key to the escape route, and the brightness just determines how many electrons get to try their luck.
Exactly. And the amazing thing is that this entire process, this mind-blowing photoelectric effect, might be better explained not by thinking of light as a particle, but through this elegant concept of resonance.
Wow. It's incredible how everything we've talked about, from microwaves to guitars, all boils down to resonance.
It really highlights how connected physics is. It's all about finding these underlying principles that explain the universe on a deeper level.
It really makes you wonder what other mysteries we can solve by viewing them through this lens of resonance.
And that's the beauty of science. Always more to explore, more to learn, and new ways to see the world.
So keep those minds curious, everyone, and we'll see you on our next deep dive.